In our previous discussion, we investigated combinations of resistances in series, which is characterized by both resistors having the same current, and in parallel, characterized by the two resistors having the same voltage. And what we found is that you could, in both cases, series and parallel, devise, with the help of a little equation that we formulated, an equivalent resistance for series and an equivalent resistance for parallel. In the case of series, it's obvious. When resistors are connected in series, you simply add the resistances. Adding more and more resistance on just makes the resistance larger and larger. And you might have expected that without any help from your local physics teacher. In the case of parallel, it was a bit stranger, because in the parallel case, when I finally devised a formula that would allow me to calculate the equivalent resistance, the formula was a bit more complicated and certainly nothing that I might guess at. Another peculiarity is that when you connect resistors in parallel, the resistance actually decreases. That is, the equivalent resistance, calculated using the formula, is less than either of the resistances. When we talked about all these things, I alluded to the possibility that I could make the situation more complicated. And that's exactly what I'm going to do today. I'm going to investigate two types of resistor networks, where you connect a bunch of resistors together. The first type that I'm going to consider is when I have a resistor in series with a parallel combination. Once I find out everything that I can about that kind of resistor network, I'm going to look at a second type where a parallel combination has a series combination inside of it. So there's basically two types. But if you are an electrical engineer, you would find yourself confronted by networks that are significantly larger and have many more elements in them. That doesn't mean any new physics, it just means more labor. And since we're not interested in working any harder than we need to understand our description of the universe, I'll just do the two types. The first type is this, clearly more complicated than any circuit that I've looked at so far. It has three resistors, a 1K, which I'll remind you is 1,000 ohms, 3,000 ohms, and 6,000 ohms. And they're connected together sort of willy-nilly in what we call a resistor network. It's not unlike a computer network. You have a bunch of computers that are connected together, and you could draw a schematic that would not look too different from this one, depending on how you configure your network. At any rate, there are no series combinations in this diagram. You say, no, Shadi, series is one follows the other. And here I have a 1K resistor and then a 3K. Those are in series. You see, they're not in series. And the reason why is that a series combination doesn't mean one after the other. A series combination means same current. And a certain amount of current is going to come out of my 9-volt battery and go through this resistor. When it gets to the junction, it will split. And I'm going to work out all the math to figure out what the new currents are. But when that current splits, only part of it will go through the 3K, which means no matter what, the 1K resistor and the 3K resistor will not have the same current. They are not in series. Nevertheless, I can look at it and say that the 3K and the 6K are in parallel because they'll have the same voltage. Let me try to convince you. That voltage won't be 9 volts because this 1K is in the way. But think of your resistors like waterfalls. The current reaches this 1K, the voltage will go down to a certain amount. But now both the 3K and the 6K are attached to that voltage, and they'll drop all the way down. You have two choices, to go all the way down through the 6K or all the way down through the 3K. Either way, same voltage. So the 3 and the 6 are in parallel. Now, ultimately my goal, if I'm not taking a test or a quiz that tells me what I'm supposed to find, my ultimate goal here is to find absolutely everything knowable about this circuit and how it behaves. In order to do that, I'm going to use a very particular strategy that I'm a fan of. If there are those in the audience who enjoy puzzling things out, like how can I figure this out, how can I figure that out, this is a little bit puzzling. It's not a difficult puzzle, but it is a little bit of a puzzle. Here's how I'm going to proceed. Since I know that the 3K and the 6K are in parallel with each other, I'm going to do that parallel combination. Whenever I have students do this, I suggest to them that they redraw the circuit. And I'll do that by taking my original circuit. This is the same one that appeared on the first slide, a 1K, a 3K, and a 6K. And I'm going to take the 6K and the 3K and combine them into a single equivalent resistor. Since they're in parallel, I use my parallel equation. Now, there's a 3K and a 6K, so I'll do 3 times 6 divided by 3 plus 6. That's 18 over 9 is equal to 2 kilo ohms. So the equivalent resistance that appears here is 2K of resistance. Now, I see that I have an obvious series combination because the current that comes out of the 9 volt will go through the 1K and will go through the 2K. So now, there wasn't a series before, but there is now. And I'll go ahead and make that series combination, which in this case is simply adding the two resistances together. So I'll take the 1K and the 2K, and it's really simple. I wrote the equation here, but come on. It's 1 plus 2 is 3K. I took that resistor network and boiled it down to the simplest possible circuit diagram that there is. One battery and one resistor. This is a circuit for which Ohm's law works. I can use Ohm's law to figure out what the current will be coming out of the 9 volt battery. And so, of course, that's my very next step. Since V is equal to IR, I'll solve that around so that I is equal to V over R, and I just have to take my 9 volts and divide it by my, warning, 3,000 ohms, because that's a 3K resistor. So that's 3,000 ohms is 3 milliamps of current. So I know that the battery is putting out 3 milliamps of current even in the more sophisticated circuit. In a sense, this 3K of resistance is what the 9 volt battery sees when it looks at the circuit. It doesn't know what's going on in the circuit. It just pushes and it can feel the resistance. And the equivalence of that resistance is 3K worth of resistance. And by the way, since I know the current coming out of the battery, for a little bit of fun extra, I said I want to find everything. The battery is cranking out a power, according to IV, that's 3 milliamps times 9 volts is 27 milliwatts of power. That is the power being supplied by the energy, by the battery, pardon me. The only reason why I bring this up is because my expectation is that as the circuit runs, the energy is going to be conserved. Because I already learned in a previous unit of this course about the law of conservation of energy. No joules will disappear in this process. If I have 27 milliwatts of power being supplied, I imagine those 27 milliwatts are going to get used in the process. But finding the current that comes out of the battery is not finding everything. What I'm going to do now that I've found out what that current is, I'm going to do the same process. I'm going to work backwards. It'll be fun. So now I'm going to do the same process I did in reverse, and to do that, I have to appreciate that this 3K resistor was the result of a series combination. I had put a 1K together with a 2K. Now remember that a series combination means same current, which means the 3 milliamps of current I discovered were running in this circuit, that's the 3 milliamps of current that are running here. That means there's 3 milliamps of current on the 1K resistor, there's 3 milliamps of current on the 2K resistor. Now, I'm about to adopt a habit that I use sometimes because I find it helps me solve circuit problems more easily. When I refer to this resistor R1, I've labeled it 1 because it's 1K. I'm calling this resistor R2. R2. I'm calling this resistor R2 because it's 2K. I have a tendency to keep things clear for myself to use subscripts that are actually equal to the value of the resistor. This works fine until you have two resistors that have the same value, and then you get in trouble. But in my notes today, I've made sure that that doesn't happen. So this little habit of mine is going to work out quite well and hopefully make it easier for us to see what's going on. Since I know that there's 3 milliamps of current running through the 1K resistor, I can calculate the voltage on the 1K resistor using Ohm's law. It would be the current multiplied by the resistance, which is 3 milliamps of current multiplied by 1 kilo ohm of resistance. Milli is 10 to the minus 3. Kilo is 10 to the 3. They cancel each other out, and it works out to 3 volts. The battery is supplying 9 volts. What I've just discovered is that when I leave the battery all the way up high at 9 volts, as high as it goes, when I cross this 1K, the voltage is going to go down by 3 volts. That's what I've just learned there. Might as well calculate the power while I'm here. The power of the 1K resistor, I'll use I squared R because I know those numbers, is 3 milliamps squared times 1 kilo ohm is 9 milliwatts of power. When I say 9 milliwatts of power, how is that energy being used up? Well, if this is just a resistance, probably it's all becoming thermal energy. It's getting hot. But it could be that this resistor represents something that does useful work. It could be an electric motor, for example, and that is where that 9 milliwatts of power is going. But I just want to keep track of the power because remember, I started with 27 milliwatts of power, and there I've just used up 9. If the law of conservation of energy holds, I only have a certain amount of power, and it's got to satisfy all of the requirements of the circuit. Now, this 2K resistor doesn't even exist in the real circuit. It was the result of a parallel combination. So that's not even a real resistor. That's a fake thing that I made up. It's an equivalence. So I still have one more backward step to do. Before I do that step, I'm going to calculate the voltage on this fictitious resistor. V2 is equal to I2R2 is 3 milliamps of current, because that's the current that runs through the whole thing, multiplied by the 2K is 6 volts. So I've got a 3 volt drop there, plus a 6 volt drop there. Oh, look, those two drops add up to 9. Makes sense. Makes sense. But the voltage on this 2K resistor is 6 volts, and it was a parallel combination. So when I take another step backwards, leading me to the real circuit that I started with, I discover that these two, because parallel means same voltage, this 3K resistor has a voltage of 6 volts, and this 6K resistor has a voltage of 6 volts, because parallel means same voltage. Since I know the 3K has a voltage of 6 volts, I can figure some stuff out. I can find its current using Ohm's law. I is equal to V over R, in this case, I3. You see what I did there? Current 3 is in the 3K resistor. My notation tells me specifically what I'm talking about. Is V3 divided by R3, which is 6 divided by 3,000 is 2 milliamps. 2 milliamps of current flow in this branch. I can also calculate the current in the 6K branch here by doing the current is equal to the voltage divided by the resistance is 6 divided by 6,000 is 1 milliamp. And does that surprise me? No, because my analysis revealed that I have 3 milliamps of current coming out of the battery, and they split into 2 and 1, which adds up to 3. It's all very self-consistent, and it makes a lot of sense. I'll look at these powers while I'm at it. The power in resistor 3, I can do I3 squared R3 to calculate that. That's 2 milliamps that I just found. Squared times 3 kilo ohms is 12 milliwatts. And I'll do the same thing for 6. In 6, the current is less. It's just 1 milliamp. And so the power is actually less, even though the resistance is larger. 12 plus 6 plus the 9 that I already found. 12 plus 6 plus 9 is the original 27 milliwatts of power. So the battery supplies 27 milliwatts, and all of these resistors, 9 milliwatts and 12 milliwatts and 6 milliwatts, use up all of that power. Either by converting it into thermal energy, which just drifts out the window, that's no fun, or by doing something technologically useful for me, like the power of the fan, which circulates the air in the room in an attempt to keep us cool. I found out absolutely everything about the circuit. I know every current and every voltage everywhere. I've investigated the power and everything checks out. That's that circuit analysis. If I added more resistors, 5, 6, 7, 8, 9, 10, I just end up with more arithmetic. I don't end up with new physics. So now I'm going to investigate my type 2 circuit. This circuit had a resistor in series with a parallel combination. Now I'm going to have a parallel combination that has a series within it. There are no parallel resistors in this diagram. Charlie, what are you talking about? This line is parallel to this line, so they're all parallel. That's not what parallel means. Parallel means same voltage. This 6 kilo ohm resistor is connected directly to this 12 volts. So I know that that potential difference is 12 volts. I don't know what these are, but together they add up to 12 volts, which means that's not 12, and that's not 12, and that is 12. There are no parallel combinations here because parallel means same voltage, and they clearly do not. There is, however, a series combination. The 4 and the 8 are in series. I'm going to do the same procedure. I'm going to whittle this circuit down until it's 1 voltage and a resistor. That'll let me calculate a bunch of stuff, and then I'll work backwards until I know everything. That's my procedure. That's what I'm doing. First step is that series combination. I'll take the 4K and the 8K and add them together in series. It's easy to do because series is the easy one. The equivalent resistance is the one plus the other is 8 plus 4 is 12 kilo ohms. So now my circuit has been reduced a bit. It's simpler looking, and now it does have an obvious parallel combination. 6 and 12 are now in parallel with each other because they're both connected to the 12 volts. The voltage there is 12 and the voltage there is 12. Now, technically, I don't have to go any further. I don't have to do this combination because if I know that that's 12 volts, then I can find the current. I know that that's 12 volts, I can find the current, and I'm going to do that. But for educational purposes, I'm going to push this thing all the way to the end and do this parallel combination in the next step. And so I'll need my equation for parallel combinations where the equivalent resistance is R1, R2, R1 plus R2, which in this case is a 6 times a 12 divided by a 6 plus a 12 is 72 over 18 is 4 kilo ohms. And so I took that resistor network, which is quite complicated, and I whittled it all the way down to a single circuit that has a 12 volt battery and a 4K resistor in it. And now I can just easily apply Ohm's law and solve for everything that I want to know by doing the process again in reverse. So what am I going to do with this? I'm going to apply Ohm's law to this situation, see if I can figure out the current. Of course I can. Beautiful numbers I've chosen to use in these circuits. Electrical engineers aren't so lucky. 12 volts and 4K. This is my simple circuit. So once again, same procedure. I'll use Ohm's law, but I stir it around and solve for the current. The current is the voltage divided by the resistance. In this case, 12 volts divided by 4,000. 4K is 4,000 ohms. Is once again 3 milliamps. The current worked out the same. Coincidentally, the current worked out the same. Because I now know that it's 3 milliamps coming out of the battery, I can calculate the battery's power, just like I did last time. Well, now the current's the same, but the voltage is larger, so the power is larger. The power is I times V, which is going to be 3 milliamps times 12 volts, which is going to give me 36 milliwatts of power coming out of this battery. So I've calculated the power, and now I'm going to unpack the circuit and do everything in reverse. This 4K resistor here is not one of the resistors of my network. It was the result of a parallel combination. And parallel means same voltage, which in this case is simple. The two resistors that created this 4K both have 12 volts of potential difference on them as I take a step backwards again, restoring my circuit. So I've got 12 volts here on the 6K and I've got 12 volts on the 12K. So the current running in the 12K resistor is V12, which is 12, divided by R12, which is 12,000 ohms, is 1 milliamp of current running there. Now, because I have 3 coming out of the battery and I've got 1 there, I'll bet you anything that the current here is 2. And indeed it is. The current going through the 6K resistor is V6 divided by R6 is 12 divided by 6,000 is 2. And that makes an awful lot of sense. The current splits when it gets to that node, the 3 milliamps separating into 2 and 1, the greatest current going through the path of least resistance. Now, this 6 ohm resistor does actually exist in my circuit. That's a real one. That was part of the original circuit. So I'll calculate its power. P6 is I6 V6, which is 2 milliamps times 12 volts, which is equal to 24 milliwatts. Right off the bat, out of my 36 milliwatts of power, that 6K is really taking up a lot of the power. This 12K that exists here is not a real resistor from the circuit. It was the result of a series combination. But I know there's 12 volts of, the 12 volts is the potential difference across the 12K. And I also know that this 12K has 1 milliamp of current running through it, which means the 2 resistors that it's the result of have 1 milliamp of current running through them. This 4K and again this 8K, they both have 1 milliamp of current running through them. So I can calculate their voltages, which is the only thing left that I don't know. I4R4 is the 1 milliamp times the 4K is 4 volts. And the voltage across the 8K is I8R8 is 1 milliamp times 8 kilo ohms is 8 volts. Oh, you look at that. 8 plus 4 is 12. Because I start up here at 12 volts, and if I go through the 6K, I go down 12 volts. I start up here at 12 volts. If I go through the 4K, it's 2 waterfalls. I go down 4, and then I go down 8, and I'm back to 0 to go to the bottom of the battery, get pumped up again, and run the circuit. I'd like to know these powers. The power in 4, I'll calculate it differently. I don't have to use I squared R. I've got 3 equations for calculating power. I squared R, V squared over R, and I times V. So I'll do I4 times V4 is 1 milliamp times 4 volts is 4 milliwatts. And the power in the 8 ohm resistor right there is I8 times V8 is 1 milliamp times 8 volts is 8 milliwatts. 8 milliwatts plus 4 milliwatts plus 24 milliwatts in the 6K resistor is the full 36 milliwatts. The power being supplied by the battery is used up by all of the resistors in the circuit. And now, by doing this resistor network analysis, I have been able to learn everything about the behavior of this circuit. This is just the first step in the direction of electrical engineering and understanding how circuits work. There are many different components. The next thing you would learn about is capacitors, and then diodes, and then transistors, and all of these things that come later. Electrical devices that have their own behaviors, their own rules, and in many cases, their own equations. This is as far as we'll go for now, and hopefully that's sort of whet your appetite for appreciating circuit analysis and circuit design, where we leverage the electrical interaction for use in our very sophisticated variety of electrical technology.